In this video, we'll continue to look at CSEC Physics past paper questions. Now, we'll be looking at January 2018, paper 2, question 1, right? So, January 2018, paper 2, question 1. So, the question says, part A, a student conducted an experiment on light traveling from glass to air. Figure 1 is a diagram showing light traveling from glass to air. The results of the experiment are recorded in table 1. So, here we have a simple a diagram of what was shown. We have light incident in glass at an angle I, and of course traveling towards air, and we're shown an angle of refraction of R, right? Now, many students, of course, would have conducted an experiment for light traveling from air into glass, and so basically when they see these results, they might be tempted to believe that something may be wrong. But of course, nothing is wrong. It's simply due to the fact that the experiment was conducted, or at least we're told it was conducted, for light traveling from glass into air. And so if you're used to seeing the angles of incidence being like whole numbers and the angles of refraction being not whole numbers in most cases, then of course nothing is wrong, because in this particular case it is traveling from glass into air and not from air into glass, as most people would have actually become accustomed to, right? All right, so we have a table which shows the angle of refraction R, and we're also given the angle of incidence, excuse me, and we're expected to complete table 1 by calculating the values of sine R and sine I. So I would have gone ahead and done that, and of course all our values of sine R and sine I were expressed consistently to two decimal places. So sine of 10 degrees, 0.17 to 2 decimal place, sine of 30, that's a half, or 0.50, sine of 50, 0.77, sine of 70, 0.94, and sine of 90, of course, 1.00. We express that to 2 decimal places as well. To the I and sine I columns, sine of 6.5, 0.11, sine of 19, 0.33, sine of 30, that's 0.50, sine of 38, 0.62, and sine of 41.0 degrees, 0.66, right? So we completed the table and would have been allotted 5 marks for doing that correctly, right? That's part 2 of part A, part 1 rather. Now part 2 wants us to use the calculated values in table 1 and plot a graph of sine R against sine I on the grid, right? On the graph paper that would have been provided, right? So we want to plot a graph of sine R against sine I. Now, once again, a lot of students would have done a similar experiment in schools to determine the refractive index of glass, and they would have plotted a graph of sine I against sine R. However, they wanted to plot a graph of sine R against sine I, so you're not always going to see something that you're accustomed to doing in an exam, so just pay attention to the instructions and do what is asked. In the end, of course, if there's an error, once you follow their instructions, then you should be getting your marks, provided you did what you're supposed to do correctly. All right. So in part 2, they want us to plot a graph of sine R against sine I on the graph to be provided. Now I would have actually gone ahead and plot the graph. I don't know how clearly this is going to be able to be seen, but I would have gone ahead and I would have plotted the graph of sine I against sine I, and of course I would have drawn my line of best fit, a nice line of best fit, virtually passed through all the points. I would have drawn my large triangle and labeled my points that I'm going to be using to find the gradient. And of course my graph has a title, I stated my scale, and of course I labeled my axes, right? So having done that, the next part of the question basically wants us to go and find the gradient of the graph. And of course, whenever you're plotting a graph in the exam, you basically treat the requirements just as if you're doing a lab. So your graph should take up more than half of the graph paper, and of course your triangle that you're using to find the gradient should occupy more than half the length of the line, right? So you don't want to draw a tiny graph in a small section and then draw only a small portion, use only a small portion of the line to find the gradient, right? So use up as much of the graph paper as possible, but of course leave some space for additional values which are outside of the range of the values that you're actually given, right? Good. So the gradient of the graph, so based on my graph, the gradient of course worked out to be 0.52. So basically, just to do a rough representation of what I have on my here. So I would have had sine R against sine I. It was supposed to give a straight line passing through the origin, right? So based on the relationship between sine I and sine R, we're supposed to get a straight line passing through the origin, and that is basically what I obtained, right? A straight line passing through the origin. So the points I used to find my gradient were the points .20, 0.30, and the point up here was 0.70, 1.06, right? So those are the points I would have used, and of course the gradient worked out to be 1.52. So of course the gradient equals y2 minus y1 divided by x2 minus x1. So this gives us 1.06. So using this point as our x2 y2, and this is our x1 y1, this would have given 1.06 minus 0.30 divided by 0.70 minus 0.20. So this gives 0.76 divided by 0.50, and that gives 1.52. Right? So the gradient of the graph works out to be 1.52. Again, due to regular experiments, would have expected something in the region of about 1.5, but of course it's not necessarily going to be exactly equal to 1.50. From this we got 1.52. Right? Now the next part of the question asks, state the name of the physical property represented by the gradient in A part 3. Now we plotted a graph of sine R versus sine I, but you have to remember that light is traveling from glass into air. And so if you plot a graph of sine R against sine I, for light traveling from glass into air, the gradient of the graph will give the refractive index of the glass. So the name of the physical property, which represented by the gradient, is the refractive index, right? So that's part B. Now part C says, explain the term critical angle. Now what exactly is critical angle? Now let's examine this little diagram right here. Now whenever light is traveling from a denser medium towards a less dense medium, the ray of light is refracted away from the normal, right? So if you look at this diagram right here, this is the angle of incidence, this is the angle of refraction. So if you just label it, so the angle of incidence, of course, is smaller than the angle of refraction due to the fact that the light ray will be refracted away from the normal. Now, at small angles of incidence, you will have an emergent light ray. However, if you increase the angle of incidence, the angle of refraction increases and the refracted ray eventually gets closer to the boundary between the two media, right? So eventually, if you increase the angle of incidence, there comes a point where the refracted ray emerges along the boundary between the two media, right? And that would mean that the angle of refraction as measured from the normal is equal to 90 degrees, right? So if you increase the angle of incidence, eventually the angle of refraction will be equal to 90 degrees. The angle of incidence for which the angle of refraction is equal to 90 degrees is called the critical angle, right? So the critical angle for light traveling from a denser medium towards a less dense medium is simply the angle of incidence for which the angle of refraction is equal to 90 degrees, right? So once again, the critical angle for light traveling from a denser medium towards a less dense medium is the angle of incidence for which the angle of refraction is equal to 90 degrees. And of course, we can only talk about critical angle if light is traveling from a denser medium towards a less dense medium. If light is traveling, say, from air into glass, then there's no such thing as a critical angle because this phenomenon or this will never occur, right? So critical angle applies only when light is traveling from a denser medium towards a less dense medium, and the critical angle, of course, is the angle of incidence for which the angle of refraction is equal to 90 degrees. Now, having said that, the there's a part 2 of C, right, which goes on to say, using table 1 or otherwise state the critical angle for the glass using A. So it says to state it, which means that we're not expected to do any calculation, or no calculation is actually required. Now, because we plot a graph of sine R against sine I, as we mentioned before, the angle of incidence is actually in the glass and the angle of refraction is actually in air. And so once again, the critical angle is the angle of incidence for which the angle of refraction is equal to 90 degrees. So simply, if we look at our table of values, we locate the angle of refraction 90 degrees, and the corresponding angle of incidence will be the critical angle for the glass used. So in this particular case, the critical angle for the glass used would be 41.0 degrees, right? Now, in some cases, if you're asked to find the critical angle and you're not given values in the table, including the 90 degrees for the angle of refraction, so let's say we did not have this value, right? How else would we actually determine the critical angle? So we could actually go to our graph and we could locate sine R equals 1 on the y-axis, right? So we basically have to draw or extend our axes to the point where it includes 1 on the sine R axis. So we go on the sine R axis and we locate the value of 1.0. We then go across to our line and we drop a vertical and we simply locate the value of sine I, which corresponds to 1.0, right? So looking at my graph, well, obviously we have it in the table, but as I said before, if we did not have it in the table, we could have actually done it from the graph. So locate the value of 1.0 and locate the value of sine I on the graph. But of course, we know that since we draw a line of best fit, the graph might not have actually passed through this point, so I'll determine the value from the graph. So from my graph, when sine R equals 1, sine I is actually equal to 0.6. Let me see, from my graph, it's actually equal to 0.66, which is what we have in the table, right? But as I said, just imagine we didn't have it. So when sine R equals 1.0, sine I equals 0.66, right? So therefore, this means that R is equal to 90 degrees, and so I will be equal to the sine inverse of 0.66, and of course, this will give us 41 degrees, right? So you won't always be given results which actually include the refraction, angle of refraction equals 90 and the critical angle, and therefore if you don't have it in the tables, you can always determine the value from the graph. So once again, you locate sine R equals 1, you go across your line and you locate the corresponding value of sine I, and of course you find the sine inverse of that, and that will give you the critical angle. So this was, well, January 2018, paper 2, question 1.